moving source equivalent to a convection current, and makes the true current circuital. 52. The above being merely to concisely explain the essential meaning of electrification in relation to displacement, and how it is to be measured. Consider a point source or charge to be in motion through a dielectric at rest. Starting with the charge at rest at one place, the displacement is radial and stationary. When permanently at rest in another place, the displacement is the same with reference to it. In the transition, therefore, the displacement has changed its distribution. There must, therefore, be electric current. Now, the only place where the displacement diverges, however the source may be moving, is at the source itself, and therefore the only place where the displacement current diverges is at the source. Because it is the time variation of the displacement. The displacement current is therefore circuital, with the exception of a missing link at the moving charge. If we suppose that the charge ρ moving with velocity u constitutes a current u ρ, that is, in the same sense as the motion, and such that the volume integral of the current density is u ρ, then the complete system of this convection current and the displacement current together form a circuital flux. Thus, suppose the charge to be first outside a closed surface, and then move across it to its inside. When outside, if the displacement goes through the surface to the inner region, it leaves it again. On the other hand, when the charge is inside, the whole displacement passes outward. Therefore, when the charge is in the very act of crossing the surface, the displacement through it outward changes from 0 to ρ. And this is the time integral of the displacement current outward whilst the charge crosses. This is perfectly and simultaneously compensated by the convection current, making the whole current always circuital. The electric current is, therefore, made up of three parts: the conduction current, the displacement current, and the convection current. Thus, J equals C plus D dot plus ρ u. ρ being the volume density of electrification moving through the stationary medium with the velocity u. If the medium be also moving at velocity q referred to fixed space, we must understand by u above the velocity also referred to fixed space. The velocities q and u are only the same when the medium and the charge move together. Thus it will come to the same thing if we stop the motion of the charge altogether, and let the medium have the motion equivalent to the former relative motion. Similarly, if there should be such a thing as diverging induction, or the magnetification denoted by sigma above, then we shall be obliged to consider a moving magnetic charge as contributing to the magnetic current, making the complete magnetic current be expressed by G equals K plus B dot plus sigma W. If W be the velocity of the magnetification of density sigma. Examples to illustrate motional forces in a moving medium with a moving source. 1. Source and medium with a common motion. Flux travels with them undisturbed. 53. In order to clearly understand the sense in which motion of a charge through a medium, or motion of the medium itself, or of both together with respect to fixed space, is to be understood, and of the part played therein by the motional electric and magnetic forces, it will be desirable to give a few illustrative examples of such a nature that their meaning can be readily followed from a description, without the mathematical representation of the results. It does not, indeed, often happen that this can be done with profit and without much circumlocution. In the present case, however, it is rather easier to see the meaning of the solutions from a description than from the formula. In the first place, let us start with a single charge ρ at rest at any point A in an infinite isotropic non-conducting dielectric, ether, for example, which is also at rest. Under these circumstances, the stationary condition is one of isotropic radial displacement from the charge at A according to the inverse square law, and there is nothing to disturb this distribution. Now, if the whole medium and the charge itself are supposed to have a common motion referred to an assumed fixed space, in the background, as it were, no change whatever will take place in the distribution of displacement referred to the moving charge. That this should be so in a rational system we may conclude from the relativity of motion, the absolute motion of the universe being quite unknown. If not inconceivable combined with our initial assumption that the electric flux and the magnetic flux not here present represent states of the medium, which may be carried with it just as states of matter are carried with matter in its motion. But as the charge, and with it the displacement, move through space as a rigid body without rotation, the changing displacement at any point constitutes an electric current. and therefore would necessitate the existence of magnetic force if we treated the first law of circuitation in its primitive form, referred to as stationary medium. Here, however, the motional magnetic force, which is the vector product of the displacement and the velocity of the medium, comes into play. And it is so constructed as to precisely annul all magnetic force under the circumstances, and leave the displacement referred to the moving medium unaffected. Or, in another form, it changes the law of circuitation referred to fixed space, so as to refer it in the same form to the moving medium. The result is h equals 0, and d moves with the medium. Similar remarks apply to other stationary states. They are unaffected by a common motion of the whole medium and the sources, and this result is mathematically obtained by the motional electric and magnetic forces. 2. Source and medium in relative motion. A charge suddenly jerked into motion at the speed of propagation. Generation of a spherical electromagnetic sheet, ultimately plane. Equations of a pure electromagnetic wave. 54. But the case is entirely altered if the charge and the medium have a relative translational motion. Start again with charge and medium at rest, and the displacement stationary and isotropically radial. Next, introduce the fact the truth of which will be fully seen later that the medium transmits all disturbances of the fluxes through itself at the speed mu times c times to the 1/2 power or square root of mu times c, which call v, and let us suddenly set the charge moving in any direction rectilinearly through the medium at this same speed, v. The question is, what will happen? A part of the result can be foreseen without mathematical investigation. The remainder is an example of the theory of the simplest spherical wave given by me in electromagnetic waves. Let A in Figure 1 be the initial position of the charge when it first begins to move, and let AC be the direction of its subsequent motion. Describe a sphere of radius AB equals Vt. Then, at the time t the charge has reached B. Now, from the mere fact that the speed of propagation is v, it follows that the displacement outside the sphere is undisturbed. It is clear that there cannot be any change to the right of B, because the charge has only just reached that place, and disturbances only travel at the same speed as it is moving itself. Similar considerations applied to the expanding sphere through this charge at every moment of its passage from A to B will show that no disturbance can have got outside the sphere. The radial lines, therefore, represent the actual displacement, as well as the original displacement, though of course, in the latter case, they extended to the point A. We have now to complete the description of the solution. There is no displacement whatever inside the sphere BDF. The displacement emanating from the charge at B, therefore, joins on to the external displacement over the spherical surface. We can say beforehand that it should do so in the simplest conceivable manner, by the shortest paths. On leaving the pole B, it spreads uniformly in all directions on the surface of the sphere, and each portion goes the shortest way to the opposite pole D. But it leaks out externally on the way, in such a manner that the leakages are equal from equal areas. The displacement thus follows the lines of longitude. This completes the case so far as the displacement is concerned. But the spherical surface constitutes an electromagnetic sheet, and corresponding to the displacement there is a distribution of coincident induction. This induction is perpendicular to the tangential displacement, and therefore follows the lines of latitude. Its direction is up through the paper above A at E, for example, and down through the paper below A at F, for example. The tangential displacement and induction surface densities, or fluxes per unit area of the sheet, say D0 and B0, are connected by the equation B0 equals mu times V times D, or D0 equals C times V times B0. Or if E0 and H0 be the equivalent forces got by dividing by C and by mu respectively, then, since mu times C times V squared equals 1, H0 equals CV0, and E equals mu times CVH0. Or, expressing the mutual directions as well, H0 equals vector product VD0, E0 equals vector product B0V, where V is the vector velocity of the electromagnetic sheet at the place considered. These last are, in fact, as we shall see later, the general equations of a wave front or of a free wave, which though it may attenuate as it travels, does not suffer distortion by mixing up with other disturbances. Now, as time goes on, the charge at B moves off to the right, the electromagnetic sheet simultaneously expanding. The external displacement, therefore, becomes infinitesimal, likewise that on the d side of the shear. Practically, therefore, we are finally left with a plane electromagnetic sheet moving perpendicularly to itself at speed v at one point of which is the moving charge, from which the displacement diverges uniformly in the sheet, following, therefore, the law of the inverse first power instead of the original inverse square, accompanied by a distribution of induction in circles round the axis of motion, varying in density with the distance according to the same law, and connected with the displacement by the above equations. In the diagram, AB has to be very great, and the plane sheet is the portion UF the spherical sheet round B, which is then of insensible curvature.